I would like to thank Dharmendra in particular, who was a good friend of mine, and I have followed the Synapse project pretty much from the beginning, and I was really impressed by the professionalism with which this project was performed, and I'm extremely glad to see all these wonderful devices here. And I think what we see these days is that there is a community of neuromorphic computing that really starts to bring neuromorphic computing to those who can use it. So far, it was mostly the PhD students that made the chips that were working with the systems. Now, for the first time, we are ready to give the systems to other people, like neuroscience, for example, but also outside neuroscience, business, finances, and other things. And I hope we are pretty much where these two guys have been more than 60 years ago. You know them, it's John von Neumann and Robert Oppenheimer in front of the machine that was built at the Princeton lab. And I call it a role model for the following reason. They used state-of-the-art devices, vacuum tubes, cathode ray tubes, mercury delay lines. And of course, all of those devices were replaced a couple of years later. And in a way, we do the same thing. We are still using CMOS for most of our systems. It's clear that CMOS is likely to be replaced, in particular when it comes to these cognitive architectures. But for the time being, it's good to use it because it's available. But what we concentrate on is the architecture. Like von Neumann concentrated on the memory processor architecture, we are concentrating on the massively parallel architecture. We concentrate on universality. We do not want special chips, but we want systems that are configurable by the users to solve a multitude of different tasks. And I think we are seeing that size matters, not in terms of cubic meters, but in terms of computational resources. If, in a very naive way, I try to categorize neuromorphic computing systems, I would say there are 4 approaches. One is to build on commodity microprocessors like ARM cores, for example. This is what the Spinnaker group and also now the Human Brain Project does, and that is a soft binary model of neural circuits. There is of course, what people do here so successfully, the custom fully digital approach where you have hard binary models of neural cells. There is the custom mixed signal approach. That is what we do in our Heidelberg group, in BrainScales, also in HPP, where we have physical models of neural circuits, and I make this little comment of being accelerated, which I will explain in my talk. There are custom subthreshold analog cells, so the purely analog approach, which is very close to biology in terms of pulse height and pulse width. So that is typically something you would use if you want to interface to real biological substrates. And there is also a new development, which I call custom hybrid. Qualcomm is an example where you really merge neuromorphic cores with conventional computing architectures. Do they have anything in common? This seems to be totally different. Well, I think what they have in common is that they are all definitely massively parallel. They all use asynchronous communication, and very, 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 very important, they are all highly configurable because we do not really know exactly how to do brain-inspired computing. We better make these systems very flexible. So there's a very important statement I want to make here, is that the complementarity of the approaches is extremely important. I think it's too early to just focus on one. It's great that we have this complementarity, and this is why we need meetings like this, so that we see what our colleagues do. In Europe, there has been a lot of activity in neuromorphic computing. One branch now focuses on the Human Brain Project, in short, HBP. There are 3 input projects that form the basis of the current HBP. That is, of course, the Blue Brain Project, which is not brain-inspired computing, but integrating neuroscience data into very detailed biological models and simulating them on supercomputers. Based on those simulations and based on other inputs, we now start to build computing architectures. And there were 3 projects in Europe that contributed to the basis of HBP. That is the Facets project, the BrainScales project, and the Spinnaker project. In consequence, in HBP, I will not describe the entire project here because I have only 20 minutes. I will focus on the neuromorphic computing. In HBP, we have 2, again, complementary concepts of neuromorphic computing: the many-core processor system and the physical model system. The many-core processor system is run by Steve Ferber in Manchester. You know him well. He uses many clocked, rather simplified ARM processors in address-based, small-packet, fast, asynchronous, low-density communication protocol, and it's effectively running in real time. So this is really a neural simulator that is very well suited, for example, to run with robots or with physical sensors and actuators. The system that we built in Heidelberg is what we call a physical model system. So we do local analog computation, but binary, again, asynchronous and continuous time, not clock, continuous time, high density communication. And the essential feature here there is an accelerated system, which I will explain a bit more in detail. As I have only 20 minutes, I will now focus on the physical model approach that we do in the Human Brain Project, and that's based on the previous BrainScales project. There are 10 rationales that are behind our work and that I consider extremely important. First of all, it is a mixed signal approach. We do local analog computing and binary spike communication. That's just like our brain. Neurons are analog devices. Action potentials are binary. They all look the same, but they have a continuous time scale. They are not synchronized, of course. Our approach is driven by architecture. We really want to find interesting architecture. We do not work on devices. We use the devices that are available. We build on what we call very high neuron input count, more than 10 or 15,000. And this is to mimic cortical neurons, which we think is very important if you want to do cortical information processing. We very much build in configurability. I said that already. That concerns the cells, but in particular also the connections. So basically what we build is a sea of neurons and synapses, pretty much like an FPGA in the digital world. And you as a user can decide how you want to wire them up and what kind of parameters we want to set. So this is universality, which is an important aspect. Scalability, of course, is the key. We always start with chips like everybody else, but then we want to scale up to wafers and large systems. We want to have an accelerated system, factor 10,000 faster than biological real time for reasons that I will explain. Plasticity is important. Upgradability with unchanged system architecture. We spend a lot of time building systems like that. So if you have the next chip generation, you do not want to redevelop all the infrastructure. So to be able to upgrade the system with the latest neuroscience inputs is also very important. Hybrid operation, interfacing with conventional computers, non-expert user access, really, really very important. We want any neuroscientist, student, computer scientist, whoever wants to do neuromorphic computing must be able to use those systems. And the objectives are rapid circuit exploration and to vary structure and to study, in particular, temporal dynamics. The chips we build, they look like all other chips. There is nothing special, but if you look to this chip, you maybe see some kind of structure. It looks like a tennis court, okay? So there are the two fields of the tennis court. Those are the synaptic arrays. In between, a very thin strip of red color, which you see here. Those are the neurons. And the message you can take home from this talk, a very important one, is if you build these systems, connectivity is the challenge. The neurons are very fancy circuits, but they don't use any real estate. You can make them very complicated. This is not a problem of occupying the space in this kind of architecture. The real challenge is to connect those neurons, in particular with the high input count that we have in mind. So all the gray stuff there, the tennis courts, those are the synapses, and the red stuff around the chip are the connections. Now what you see is scalability is a problem here. If you want to go off chip and connect to the next one, you need these silly little bond wires, which you see here on this, on this photo. So what we did right from the beginning is that we said, well, we don't want bond wires. We want to do wafer scale integration. We want to leave the wafers intact and have these little elementary chips, the high-end chips on the network, and of course all the synapses and the connections. That requires a lot of technology development, in particular having a post-processing layer to build networks which are as large as the wafer. So we have solved all these problems. And today we have wafer-based systems that carry 50 million neurons and about 200,000, 50 million synapses and about 200,000 neurons with plasticity mechanism, short-term and long-term plasticity, highly configurable neurons and synaptic parameters, and an acceleration factor of 10,000 beyond biological real time. If you build a chip or a wafer, then you're not done. You have to build a system, as you see very nicely here. This is a computer drawing of our system. You see that the wafer is connected to many printed circuit boards. So at the bottom, you see piles of FPGAs that we use to input and output data. You have to bring power in, data in, and data out. And a lot of effort went into building this system. This is a computer drawing. So in real life, the system is ready now. We are having these systems, and for the Human Brain Project, we are now building 20 of them. This is one of the boards, which is about that size, and under this cooling, copper cooling element, is one of these 20 centimeter or 8-inch wafers. So the system that's currently now under construction in Heidelberg as a physical model system is the one you see here. So this looks rather boring. It's a set of racks like any other computer, but it carries these 20 wafers. And another thing that looks boring in the middle are conventional computers. There's a pile of really state-of-the-art, off-the-shelf computers. So why am I referring to them? The reason is that they are very low latency, very high bandwidth local computers that we can use to run closed-loop experiments. Those are the systems that provide the data that the system is going to analyze. I have to show you this picture. So we built a little container at the back of our institute, at the backyard, where we have the control room and seminar room and workshops. And in the blue corner that you see here, we built what we call the HBP NMPM1, which is a very complicated abbreviation. It means Neuromorphic Physical Model Phase 1 System, and I will show you the upgrade plans on one of my last slides. So what is the performance of the system? Let me refer to energy and time, and then give you some examples on experiments that we run with still single-chip systems, I have to say. The Wafer are now being commissioned. One is the energy. Often people talk about power. I think energy is the better thing because energy is what you pay to your electricity company. And so energy you have to normalize, of course, to some kind of time or better to an elementary operation. And an elementary operation that is very useful, I think, in neuromorphic computing is, for example, a spike or asynaptic transmission. If you look for the price you pay for a synaptic transmission in your brain, it's 10 femtojoule. If you go to high-performance computers like Henry Markram's very detailed model, it's a joule. So there are 14 orders of magnitude. The systems of HPP, the Spinnaker and the BrainScales system, they sit at 10 to the minus 8 and 10 to the minus 10 joule. These are real numbers, including all the overheads and inefficiencies of power supplies, cables, FPGAs to read out and control the system. This is not a measurement done on a single synapse. It's really using the entire system and dividing by the number of elements. Timescales I consider even more important because simulations on supercomputers, which are very useful for neuroscience because they are so configurable, have a big problem. That if you want to simulate a day, for example, of learning and plasticity, it takes typically on a supercomputer a factor 1,000 more. And 1,000 days is 3 years. That's the time of a PhD thesis. So if you want to repeat experiments in a closed loop, for example, by reconfiguring the system, that is a hopeless enterprise. If you ever want to attack development, which I think is a key, I mean, to attack development of these systems is really one of the major scientific issues, also for applications later, then that is totally inaccessible. It would take you thousands of years to do this. This is why we built this accelerated system, which at the same time can run synaptic coincidences at the level of a couple of nanoseconds, and then running a system for tens of seconds or thousands of seconds or hours, you can even address developmental timescales. Usability is another thing. As I said, you have to build a system that is useful by non-experts. So we did a lot of work in the previous Facets and BrainScales project to develop configuration languages, very much like people do here in IBM. So there's a very nice parallelism which you see. We developed the Pine language, which is a bit like Verilog for neuromorphic computing. It's there to describe networks. Then we have a place and route system. We can simulate our system, and we have all the infrastructure for remote access to this neuromorphic system. At the last Human Brain Project Summit in Heidelberg, which was a month ago or so, for the first time we demonstrated this remote access from our lecture hall where Andrew Davison from GIF Surivet gave the talk, and he submitted jobs to the neuromorphic system sitting in Manchester and in Heidelberg. And as you see, the laptop is somewhere in Portugal, so you can sit on the beach and hopefully then at some point run your experiments on these large-scale neuromorphic systems. Applications. I will spend now the rest of my time with applications. There are many, many applications now. We have published quite a few papers. Let me just go through 3 or 4 examples. One is reverse engineering biological systems. So typically what you can do is you know from biological data that there are some concepts which are realized, like, for example, winner-take-all circuits, decorrelation units, lateral inhibition, and things like that. This is an example where we copied, and that is work not done by our group, but by a neuroscientist, Michael Schmucker and Martin Navrot, who at that time were at the Bernstein Center in Berlin, and they had a model for the olfactory system of insects, which seems to be very special, but it's an interesting one, because what it does multivariate data analysis. So you have the sensors that react to certain chemicals, and then the combination of those chemicals, that is then assigned to certain flower types, for example, roses and tulips and whatever. This is what the insect does. So there is this circuit which we can, even for a neuroscientist, it's possible to implement that on our system using this Pine language. This is a typical experiment which we do where you see spike patterns. You will see more spike patterns in real life here on the IBM system. We do the same thing. The only thing I would like to point to is at the bottom of this raster plot, the little dots are the spikes. You see the input data, okay? This doesn't really work it doesn't show. So at the bottom there, these sort of very bizarre and very randomly looking dots. Those are the input data, and you have to find the correlations and the associations in this input data. And of course, you have to go through a training step. Left is before training, right is after training. And what you have to look at is at the upper corner of the right plot, there are these two rate spikes arising, and this is a demonstration that the learning has actually worked. Why is that interesting? Well, of course, you can do that on a laptop. There is nothing special about doing multivariate data classification, but it has interesting features. One is the low energy, the other is the high speed, but there is one other thing, which is also these systems are able to work with imperfect circuits. These are analog circuits, and this is a typical characteristic of neurons. It's input rate versus output rates, and it should be linear, and you see it is more or less linear. But it's a disaster because the slope is different from neuron to neuron, and there are also huge offsets. So the variability is typically 20 to 30%. Of course, by using the configurability of the circuits, we might calibrate them. We make them all equal. That's in principle we could do, but it's a huge effort. But what we have shown in this paper is if we don't do that, if we use uncalibrated circuits and population coding, we can solve the problem just by using more neurons. Okay? Two more applications, closed loop experiments. We are now running closed loop experiments, integrating the wafer into this computer system where we use all the high bandwidths that we have to run the experiments. And the typical experiments that we now do is that we have a simulated environment on the computer, simulated actors and sensors, and then we have in the environment, for example, a force field, which here happens to be where the velocity is proportional to the force k and the distance, and the task is to track a point or to move it to a certain position in a closed loop experiment, and that now starts to work very well. Using plasticity is another thing. Typical example that I can shortly demonstrate here or show you is the localization of sound sources. You know that owls, for example, birds are able to localize sound sources by measuring the phase difference between the left and the right ear. There is a neural model for that. We can implement that on our system using STDP. We can run experiments. Here you see the learning process. The colored plot there at the left corner is the learning process, the change of the synaptic weights. And the owl, the bird, does echolocation with a precision of roughly 100 milliseconds because of the acceleration. We can do that with typically 10 nanosecond precision. That means we have a phase detector with imperfect synapses and neurons with big variability that works to the precision of nanoseconds, which, for example, has a very interesting application in automotive. For example, you can use this to locate ultrasound sources. Stochastic computing is a very, very interesting thing, driven not so much by biology, but by theory. Okay, you have all seen this picture. If you look at it, you see there are two solutions to the riddle here. You can see either a duck or a rabbit, but never both at the same time. And there is a theory behind this, which says what we do in our brain is what we call stochastic sampling. So somewhere in your brain, and you learn that by looking at such animals before, you develop a stationary probability distribution. And what we have shown together with others is that you can implement such probability distribution in neuromorphic circuits, and that you can even understand the flipping time between the two images. This is the gamma distribution, the one you see there on the right corner. So it takes some time to flip between the duck and the rabbit. And we have shown that there is this kind of theory. You can actually demonstrate that you understand this process, and you can use it for computing using these systems that we have. As a short remark, how can you do stochastic inference with deterministic neurons? Because our neurons are deterministic systems. They are not quantum mechanical or anything like that. Well, what we do is we use the background noise in the circuit to provide the stochasticity. And there's a paper out there which you can look at. This is an example where you let the network explore the space of 3 numbers, for example, and like you, always sitting either at the duck or the rabbit, here the system sits either at the 0, the 4, or the 3. Let me shortly comment on the roadmap of the future. HPP has been reviewed recently, in particular for the next plan, which reaches out to 2023. This is a book, which I have only one copy here, but of course you can look at it on the web. And so we have several upgrades. One is to provide what we call algorithmic synaptic processing. So we want to put RISC processors on each of our little chips to be able to implement plasticity mechanisms. The other is implementing multi-compartment neurons. Prototypes are available now. That means we have dendritic branching, signal dispersion, which are passive features, but also dendritic spikes and back-propagating action potentials. This is a very important thing for temporal sequence learning. There is a plan in this book. I know that you cannot read it now, but you can look to the book on the web. And what you will find is our roadmap, which reaches out to September 2022 here. And what we want to build is a 5,000 wafer system with all the features, in particular, the much improved plasticity mechanism implementation by these plasticity processors, for which we have a prototype now. Let me close by making one last comment. We are also going public. Again, this is what I see IBM is doing now, which is really important. We have these big systems, which are, in a way, the supercomputers of neuromorphic computing. But it's important that people start to play with this also outside the big projects. So what we do is we have these little chips, individual chips, not wafer chips. Both groups have that, the Spinnaker group and the Heidelberg group. We are putting them on little USB boards, and we are going to sell them as of next year. We are now setting up a Kickstarter activity to get this financed, and it comes with a complete development set with software and this little hardware thing which you can plug into your laptop. It has analog input, analog output, digital input and output. It even has Bluetooth and wireless LAN on board. So this is my conclusion. Neuromorphic computing, I think, is a very consistent concept for non-von Neumann and also non-Turing computing architecture. It's accessible to available technologies. That's the important thing for the time being. Like von Neumann used the vacuum tubes, we are using CMOS. So once there are better components available, like resistive memory, for example, we are ready to implement it, but at the moment, we do not care about it. We watch the market, and once it's there, we will use it. The key features are universality, scalability, fault tolerance. I have shown that, power efficiency, speed, and most importantly, the ability to learn. The accelerated operation of the system that I showed, to my knowledge, is the only known approach to bridge all timescales relevant for circuit dynamics. And the very last slide is one I like very much. HPP has been criticized a lot. Some of you may know that. And so I'm glad to show you that the consortium is actually a very lively and active one, and it's a big consortium. This picture has been taken in Heidelberg at the HPP 2014 summit. So you see, this is not even all people, but you see a good fraction of the project. And the amazing thing, and this is a mystery to me, if you look to the shape of this group, okay, does it remind you of something? It looks a lot like Switzerland for those of you who know the European map. But that's a complete coincidence, of course. Thank you very much.